From knowledge bases, to ontologies. This is episode 5, the formal stack. In the last 4 episodes we have been circling something, calling it formal, calling it machine-readable, calling it precise, without ever quite showing you the machinery. So today we open the box. There are 3 core languages that turn an ontology from an idea into something you can actually write down, and a computer can actually read: RDF, RDF schema, and OWL. They stack, each one building squarely on the last. By the end of this episode, that whole stack will feel like home. Here is the shape of the entire episode, in a single picture. 3 layers, stacked one on top of the other. At the bottom sits RDF, the layer of raw facts, where every statement is reduced to one simple form. In the middle sits RDF schema, which we will just call RDFS, the layer that adds structure, classes and hierarchy. And at the top sits OWL, the web ontology language, the layer of real logic, rich enough to express genuine reasoning. As you climb this stack, 2 things rise together. Expressiveness, how much you are able to say. And complexity, how hard it becomes to compute. Hold that trade-off in mind, it is the quiet theme of the whole hour. Before we touch the first layer, it is worth knowing what the whole thing stands on, because none of this was conjured from thin air. These standards rest on decades of mathematics. Set theory gives us classes and membership, the idea of a thing belonging to a category. First-order logic gives us the language of statements, and, or, not, for all, there exists. Description logic, a carefully chosen fragment of that, gives us something both expressive and still decidable, meaning a machine can always finish reasoning over it. Graph theory gives us the picture of nodes and edges. And database theory gives us schemas and integrity. 5 deep, well-worn foundations, and the formal stack is simply where they finally meet. So let us start at the very bottom, with RDF, the resource description framework. Its single idea is almost shockingly simple, and that simplicity is precisely its power. Every piece of knowledge, however complex, is broken down into a triple, 3 parts. A subject, a predicate, and an object. The subject is the thing we are talking about. The predicate is the relationship. The object is what it relates to. Jack Ma, founder of Alibaba. That is one triple. One fact. It reads almost exactly like a short English sentence, and that is no accident at all. The triple is the atom of the entire semantic web, the smallest unit of meaning, from which everything larger is built. And here is the genuinely beautiful part. Everything is a triple. There is no second mechanism, no special case waiting in the wings. A million facts about the world are simply a million of these little subject-predicate-object statements, linked together. To keep them globally unambiguous, every single name is a URI, a web address, so that your Alibaba and my Alibaba are provably the very same thing, anywhere on Earth. And when you connect all of these triples up, you do not get a table of rows and columns. You get a graph, web of nodes joined by labeled edges. That shift, from rigid tables to a flexible graph, is exactly what lets knowledge sprawl, and merge, across the whole open web. Raw triples are powerful, but on their own they are flat, they know nothing about kinds of thing. So we climb to the second layer, RDF schema, which adds precisely that. RDFS lets you state 3 new kinds of thing. First, subclass of, a student is a kind of person, which builds a hierarchy of classes. Second, domain, the subject of teaches must be a professor. And third, range, the object of teaches must be a course. With just these 3, the machine gains the power of inference. Tell it merely that someone teaches something, and it can now conclude, entirely on its own, that they are a professor. Quietly, structure has turned into reasoning. Let us watch that actually happen, concretely. We declare that student is a subclass of person. We declare that the property teaches has its domain set to professor, and its range to course. Now we add a single, bare fact: Dr. Lee teaches logic. Notice what we never said. We never said Dr. Lee was a professor. We never said logic was a course. And yet the machine now infers both of those, automatically, from the schema alone. This is your first real taste of what makes an ontology more than a database. A database stores only what you put into it. An ontology, even at this modest RDFS level, can hand you back facts you never explicitly wrote down. Powerful as it is, RDFS is still fairly blunt. It cannot say that two classes are mutually exclusive, or that a property has an exact count. For that real expressive power, we climb to the top layer, OWL, the web ontology language. And OWL actually arrives in three flavors, where the choice between them is a genuine engineering decision. OWL Lite is the simplest, meant for basic hierarchies. OWLDL, the DL standing for description logic, is the sweet spot, maximally expressive while remaining fully decidable, which is exactly why most serious ontologies choose to live there. And OWL Full is the most expressive of them all, but it surrenders that guarantee of decidability. More power, more cost, there is that trade-off once again. So what does OWL actually give you, over and above RDFS? It hands you a far richer vocabulary for stating truths about your domain. You still have your classes, your properties, and your individuals, the specific instances. But now you can write real axioms about them. You can declare two classes disjoint, nothing can be both a person and a building. You can state cardinality, a course has exactly one primary instructor, no more and no fewer. You can declare two things equivalent, that your notion of lecturer is precisely my notion of instructor. Each of these is a hard logical constraint, one that a reasoner can check, and then use, to surface contradictions and draw conclusions you would otherwise have missed entirely. Let us make all of this real, by reading an actual ontology, line by line. We are looking at a tiny university domain, written in Turtle. First come the prefixes, short nicknames for the long standard vocabularies, OWL and RDFS. Then we declare our classes, course is an OWL class, person is an OWL class, and professor is a subclass of person. Next comes a property, teaches is an object property, with its domain set to professor and its range to course, exactly as we discussed a moment ago. And finally a restriction, every course must have at least one teacher. Notice the crucial thing. This short, readable block is not documentation about the system. It is the system. A reasoner loads precisely this, and begins drawing conclusions. And there is still more in OWL's toolkit, well worth meeting briefly. Equivalent class lets you bridge two vocabularies, declaring that lecturer and instructor name the very same set of people, so that facts about one instantly apply to the other. Disjointness draws a hard line, stating that undergraduate and graduate can never overlap, so any individual claim to be both raises an immediate contradiction. And cardinality restrictions pin down exact counts, a student enrolls in at least one, but at most 6, courses a term. Every one of these is a sentence in formal logic. And because it is formal, a machine cannot merely store it, it can actively reason with it. So let us stack the 3 layers back up, and take in the whole structure at once. RDF, at the base, gives you the facts, the raw triples. RDFS, in the middle, gives you the schema, the classes and the hierarchy. And OWL, at the top, gives you the logic, the rich axioms and the reasoning. Each layer strictly contains the one beneath it, nothing is ever thrown away as you climb. And running straight up the side is that one persistent trade-off. The higher you go, the more you can express, and the more it costs you to compute. Expressiveness and complexity, rising together, hand in hand, the whole way up. Which raises the genuinely practical question, which layer should you actually reach for? And the honest answer is, the lowest one that does the job. If all you need is to publish and link data, to connect datasets across the web, then plain RDF, with a little RDFS for structure, is very often plenty, light, fast, and easy to maintain. But the very moment you need real reasoning, automatic classification, consistency checking, inferring facts that were never stated, you reach up for OWLDL, that decidable sweet spot. Do not pay for logic you will never use. But when correctness truly matters, the expressive power is right there, waiting for you. And that, in full, is the formal stack, 3 languages, 1 rising tower. RDF for facts, RDFS for schema, OWL for logic, with expressiveness and complexity climbing together all the way to the top. You can now read an ontology, and know exactly what each line is doing. But building one is only half of the story. Next time, we put it to work. Episode 6, Query, Validate, and Build, where we meet SPRQL, to ask questions of our graph, Shackle, to check that our data behaves itself, and the tools, from protege to large language models, that finally bring an ontology to life. See you there.